Hello and welcome back to another talk, another lecture on the advanced plasticity of solid continua, an NPTEL course. You will recall from the last lecture that we have been discussing about rate independent plasticity but with pressure sensitivity. Specifically, we were discussing about the Drucker-Prager model, and we first started off with phi star, the dual potential, not phi as in the usual cases, and from there we derived phi, the dissipation potential, and then using the dissipation potential added to the elastic part of energy, we constructed a final potential function script j or something whose minimization would lead to a variational framework to determine the plastic strain increment given the input strain increment. Okay, so this was where we stopped the last lecture. In today's lecture, therefore, we start with how to do that minimization, right? So recall from the last lecture that we had this functional j, right? We already wrote this functional j here, right? But we will repeat it here, so don't worry about it. So now our objective is to determine the plastic strain increment given the strain increment delta epsilon, okay, that you have somehow found, right, or you may have applied that particular strain, right. So, so recall that our dissipation functional had this form, right, phi of eta is equal to k times norm of eta 0, right. If this constraint is satisfied, which is trace of eta is less than or equal to 3 alpha times norm of eta 0, okay. This came automatically when we actually determined the dissipation potential. Please recall that. If required, go back and go through that lecture once more, the last lecture. And otherwise, if this constraint is not satisfied, then phi of eta is infinity. In the last lecture, instead of phi of eta, we talked of phi of j. You know, eta or j as the argument, it does not matter, right, because after all we minimize something. So finally, right now eta or j is just a placeholder. So for isotropic plasticity, as we have been working with small deformation isotropic plasticity, we know that there are only two material constants, the Lamé parameters mu and call it kappa, one mu being the shear modulus and kappa being the bulk modulus, right. So C inner product with eta can be written as 2 mu eta 0, the deviatoric part of eta is eta 0 plus the volumetric Lamé constant kappa, which is the bulk material modulus times trace of eta times I. Okay, so this is the requirement. Even when it is plastic strain increment, the same relationship is valid. As I have already told you that in this logic of plasticity, elasticity is always valid except that plasticity produces an extra constraint, that is all. So material modeling is the same as in elasticity, right. The rest of it, the flow rule etc. automatically is derivable, right. So therefore, we actually can write the elastic part of this functional j, script j, in terms of the Lamé parameters this way, okay. This should be clear to you. This is just an expansion that I have done. If you are not directly comfortable with this, please do that yourself, do that expansion and convince yourself that this is true. So therefore, the objective functional now becomes this. Okay, so now see that the input strain delta epsilon has two parts. One is delta epsilon 0, the deviatoric part, and the other is delta epsilon v, the volumetric part. There are two parts to it. So basically, mu is associated with the deviatoric part, the Lamé constant, kappa is associated with the volumetric part. So therefore, basically we have got this clean separation of terms. This is corresponding to the deviatoric part, this is corresponding to the volumetric part, and this is the dissipation potential still lying intact in the expression. Now, as before, as we have already been doing, always been doing, define the trial stress as script C, inner product with delta epsilon, and also extract from there the deviatoric part of the trial stress, which is 2 mu times delta epsilon 0, and also the pressure part, which is P trial equal to kappa times delta epsilon V, right. Now, this is the optimality condition as before. So, 0 belongs to delta script j as a function of xi. Xi or eta, it does not matter, because this is just a placeholder, right. So, we have to actually differentiate. In this particular case, because of the smoothness of this functional, we can say 0 equals, this statement is nothing but now 0 equals grad of j, script j, I am sorry, script j of xi, right, grad with respect to xi, grad with respect to xi. Okay. So, so let us actually compute this. Now, you will recall that script j had two parts, one is the elastic part. So, let us do that differentiation with respect to the elastic part, for the elastic part with respect to xi, of course, first, and we get the standard relationship. We have been doing this for quite some time, that sigma, you get that the stress, you get back the stress in terms of the incremental strain minus xi. So, this is C times incremental strain minus xi. Okay. So, now actually, so you can see for yourself from this expression that sigma will be actually equal to sigma trial, which is assuming that sigma trial is of this form, sigma trial is of this form. This is the deviatoric part of sigma 0 trial, but the sigma trial is actually this form. So, use that form here and replace this C inner product delta epsilon by sigma trial. So, you have this. Okay. Now, observe that. So, let us proceed forward. We now need to do the subdifferential, basically gradient for the other part also, phi of xi. Now, phi of xi is of the typical form k times norm of xi 0, recall that, subject to the constraint that we will come to. The constraint is a very important constraint, the volumetric constraint, which will come, right. But first let us do this, which is very simple. For if xi 0 is not equal to 0, then you have this k times xi divided by norm of xi 0 divided by norm of xi 0, giving you the differentiation of phi with respect to xi 0. Okay. Now, let us look at this constraint. Trace of xi has to be equal to less than equal to 3 times alpha times norm of xi 0, right. This must be active during the plastic flow, all right. This constraint must be active during the plastic flow. And we have already discussed earlier, that this constraint essentially comes as an equality, that you should recall, all right. Without that equality, you really do not get a non-zero plastic strain, right. Anyway, so define the plastic flow direction for the time being. This is, even though I call it the plastic flow direction, this is the plastic flow direction corresponding to only the deviatoric part. Remember that this is not the overall plastic flow direction given here. Np equals xi 0 divided by norm of xi 0. The associated flow rule, therefore, I can write as lambda times Np plus alpha I. Lambda is still not determined. Okay. So, basically, you see that now the direction of the plastic flow is not just Np, but there is an extra term alpha I. Why is it associated? It is still the normality rule, because if you differentiate del phi, if you differentiate phi, then we saw that there are two terms. One is just this term Np times something, and the other term is alpha I, because of this subdifferential with respect to the indicator function, which accounts for this constraint, and that indicator function becomes valid, non-trivial. The derivative of the indicator function becomes non-trivial only on the boundary where this constraint becomes an equality. All this you must recall. Okay. So, we therefore have xi 0 equal to lambda np, trace of xi is 3 alpha lambda from that split, right. Now, use the fact that sigma is sigma trial minus C inner product xi. So, take the deviatoric part of the whole equality and you get sigma 0 equal to sigma 0 trial minus only the mu part of the C inner product xi, because the other part corresponds to the volumetric change which does not come in the deviatoric part, right. So, therefore, now we can actually substitute xi 0 here from here, lambda np here, to get sigma 0 equal to sigma 0 trial minus 2 mu lambda np, right. Now, pressure is clearly given by the pressure trial minus similarly kappa times trace of xi, right. So, now recall from trace of xi this expression 3 alpha lambda, and observe that I can write this as P trial minus 3 kappa alpha lambda, all right. Now, clearly NP corresponds to sigma trial, sigma 0 trial, the deviatoric part of the trial stress. So, I can actually write that is NP is also equal to sigma 0 trial divided by the norm of sigma 0 trial, all right. So, now I can write the overall norm of sigma 0 to be equal to the norm of sigma 0 trial minus 2 mu lambda, right, because of this last expression that we actually had for this sigma 0, right. Okay. So, now substitute all this in the yield condition, in the yield function, yield equation. Only when, so you basically get this sigma 0 trial minus 2 mu lambda, this gives you norm of sigma 0, right, plus 3 alpha times p, p is given by p trial minus 3 kappa alpha lambda equals k. Equality has to be maintained because other than that there is no plasticity, right. Expand and collect all the lambda terms. So, this is what? This is just a rearrangement. Find lambda, this. Once you have found lambda, right, then lambda has been found purely in terms of things sigma 0 trial because you assumed it to be the trial stress, assuming a purely elastic step, right, as in our earlier cases. P trial again assuming a purely elastic pressure. K is a material constant, alpha is a material constant, and all that. So, lambda can be found, and once you find lambda, you recall that our new plastic flow direction overall is given by NP here plus alpha I because of the deviatoric volumetric part, pressure part. So, it is lambda times this, all right, which gives you delta epsilon p. Right. So, this is basically the overall way of determining the plastic strain increment for the this can be implemented within a finite element program, but I am not talking right now of implementing this directly in a finite element code, because when I talk more in a more general setting, then in that context if I talk of the finite element implementation of all this, then these kind of settings come as specific cases. That is the reason why I am only telling you how to determine delta epsilon and not actually putting it in a strict finite element methodology, right. I will be discussing it soon, but in a slightly more general setting. The starting of this general setting is our discussion first, our introduction to rate dependent plasticity. Now, rate independent plasticity is basically a special form of rate dependent plasticity. So, therefore, let us understand rate dependent plasticity to be a more general form of plasticity, right. So, we will discuss this carefully. Now, so far in rate independent plasticity, we have always been working with a very specific, a sharp yield surface. That yield surface may have been expanding, that yield surface may have been translating as in kinematic hardening, but at any given time there is a very well defined yield surface. You cross it and you are in an unnavigable trajectory. That means stress cannot cross the yield surface, it can only lie on the yield surface to create plastic flow. This is where the rate dependence comes in. It is actually bolstered by experimental investigations, experimental evidence, and also physical considerations, which I will come to. But it does not admit any such sharp yield surface. It may admit a yield surface, so called yield surface, but stress can move beyond that yield surface. So far, if there has been a yield surface, stress always used to remain here, and the flow direction used to be the normal to that yield surface, the normality rule, or if in case of non-smoothness, the normal cone. All the elements within that normal cone would have given us all the possible directions of the plastic flow, right? But no more, no longer. Normality rule is still valid, that is another matter, but it is not. So, stress now need not be restricted to the yield surface, it can cross. So, basically stress can be somewhere here, and this extra thing that you see of the stress which is jutting out beyond the yield surface is called the overstress. So, overstress is allowed in rate dependent plasticity. Okay. So, so you can still have an yield surface. You can actually need not have an yield surface, have a yield surface in some cases of rate dependent plasticity. We will discuss that. Okay, there need not be any yield surface, but if there is, then stress can move past it. That is what is important. Okay. Why is it like that? Why is it that rate dependent plasticity is so important? Rate independent plasticity is only theoretically valid. Theoretically, it is a theoretical I would say rate independent plasticity is a theoretical curiosity. It is not what actually happens in materials mostly. Why is it? Because plastic flow is basically a kinetic process. Why is it? Kinetic process means it is not just the reorganization of the microstructure that is at play. It is also the corresponding force like terms that come into play. Without appropriate thermodynamic forces, there is no reorganization. So, if there is a reorganization, there is a force like object, stress like object, right. So, the process is not entirely kinematic, it is kinetic. So, think of all these cases: dislocation glide or climb in crystalline solids, diffusion assisted rearrangements, thermally activated slip events, various microstructural rearrangements in amorphous materials like gels, polymers and things like that. These are all energetic, there is an energy in it. Thermally activated slip events, thermal effects are actually derived from heat. Heat is a form of energy. Energy cannot be only kinematic. It has to have both kinematics and forces, right, associated with it. Otherwise, you can't create energy. So, if that is the case, then what we get basically is that we must overcome these energy barriers by use of forces. So, right, so there should be driving forces coming into play. If you call this by sigma, and if you call all these rearrangements appearing in epsilon p dot, microstructural rearrangements, assuming that it is all appearing in this plastic strain rate, then it has to be a kind of a function of sigma, and that should be such that whenever sigma is not equal to 0, you should be having some epsilon p dot, or it may be so happening that for some sigmas you may not have actually any epsilon p dot, but beyond a certain value of sigma onwards you will be having epsilon p dot, but that will go on changing, because according to the function g, that sigma will continue to evolve as epsilon p dot evolves. According to this g, sigma will also evolve, but g may get fired to be a non-zero function only if sigma crosses a certain threshold. That is possible. It may not even require a threshold in some cases, right, Wherever you need a threshold, you have the condition, again the yield surface coming into play to play a role in rate dependent plasticity as well. Otherwise, there is no need for any notion of a yield surface. Okay. So, you see, all that we are talking of is a continuous dependence of epsilon p dot, the plastic strain rate, on sigma. Continuous dependence, right, at least beyond a certain threshold value. So, this new worldview therefore tells you that plastic flow does not begin at the yield surface. At the yield surface, it should still be close to 0 in this new worldview, because it has to continuously change. If there is a yield surface, below that there was no plastic flow. So, on the yield surface it is still 0, it is increasing beyond the yield surface in a continuous manner as epsilon p dot increases, right. So, this is the physical perspective of rate dependence. So, you should remember that. So, now let us talk of the time scales because of which rate dependence can come. Rate dependence, a rate independence of course assumes that the microstructural rearrangements, all these dislocation, motion, glide, climb, getting stuck while moving, it may get stuck at the interfaces of let us say grain boundaries and things like that. All these processes are happening very fast, so fast that when you actually look at this clock, this kind of a clock, it takes no time. So, that means it is infinitely, the microstructural arrangements are infinitely fast. But that may not be the case in multiple scenarios. For example, a clear separation of this macro, this clock shows the macro time, let us say, right. So, this clear separation of the macro and micro times may not always be possible. For example, think of a situation in which you are using a dynamite to explode some rocks, right. So, that is a high strain rate deformation event for rocks, and high strain rate means strain changes by a lot over even a very small time. That means the time scale, because if I am interested in a finite change in the strain value leading to a finite change in my deformation, and if that is happening in a very small time, then that small time may be very close to these microscopic time scales. You never know, right. So, therefore, there is no such clean separation. The clean separation between the macro and microscopic time scale is gone, right. Similar situations happen, exactly the same situation under different types of dynamic loading conditions also. Need not be a blast all the time. It can be an impact, it can be dynamics happening at a very high rate, right. Or it may so happen with creep and long term deformation also. Creep typically happens, some types of microstructural rearrangements takes a lot. So, this is another way of looking at it. So far we have been talking of microstructural rearrangements happening very fast, but it may so happen that the microstructural rearrangements are themselves happening very slow. This is what exactly happens in creep, right. So, then it is obviously comparable with my clock time, right. So, basically this is also the case. Here again we go back to the original situation in which the microstructural rearrangements are fast, but your temperature, let us say, is very high. So, you will also see in your experiments things developing fast, right. So, no clear separation of these two scales once more. These are different scenarios. So, we can actually go on expanding upon this, but you get the point that a clear separation of the time scales may not always be possible. So, therefore, yeah. So, rate independence should also be looked upon as a kind of a discontinuous kind of a scenario, describing a discontinuous physical scenario that some observers may say that I find it difficult to deal with this kind of discontinuities. For example, a sharp yield surface, an infinite gradient, for the identity function which is 0 inside the deal set, outside it is infinity. I find it difficult to deal with it. Numerically, of course, it is a difficult thing. That is why you need all this kind of return mapping and things like that. So, here the plastic strain rate will be, in the rate dependent case, this is no longer the case. That means the rate dependent cases envisage a scenario in which you have, unlike the rate independent case where phi star was always an identity function, now you have a smooth phi star. So, earlier phi star was an identity, right, it was like a bowl exactly like this, it was 0 here, this is my set C, for all sigma in C it was 0, phi star it was 0 here, this is 0, right, and it was infinity, just outside. So, outside everywhere it is infinity. Okay. Now, it is no more like that. So, now phi star will be more like something like this. Okay. Well, it can be very steep here, but still continuous enough to approximate this, right. So, this is what we are looking at. We are actually looking at a amelioration of the discontinuity, replacement of it by continuous functions, smooth functions, right. Phi star reflects that. So, plastic flow therefore is envisaged in this case to be gradually increasing with stress. Stress strain therefore relationship is smoother and hence more realistic hopefully, right. Now, look at the dissipation potential. Dissipation potential earlier was of what form? Like this, correct. This was my phi, this is phi, correct. You remember that it was an inverted tent function, but now this is not true. You will, if you just take, if you start with this phi star, the smooth phi star, and do a Legendre transform, you will see that this will become something like, okay. So, it is no more an inverted tent, but it is a smooth, like a function like an x square, right. So, now we have a, so unlike the earlier case when this was an inverted tent, you see this was not strictly convex. Why not? Because you take 2 points on this inverted tent. Any other point you take in between, it will be remaining on that boundary line only, it will not be inside. But on the other hand here you take for a more realistic function like this, for example here you take 2 points, one here, the other here, in between this line will be strictly inside, right, this joining line will be strictly inside. So, therefore, this is one of the important things that we have now strictly convex functions. We are dealing with strictly convex functions, not barely convex functions, just convex functions. You understand, right? This is the difference between strict convexity and just convexity, right. Just convexity does not require you to be strictly convex, even though strictly convex function is also convex. Okay. Now, let us also talk of the thermodynamic consistency, but this I will not be pressing much because I will not be talking much about the Onsager kind of thermodynamics here, but we just observe that general irreversible processes typically are represented by strictly convex dissipation potentials. For example, you can think of phi as a function of epsilon p dot to be of the type scaling like epsilon p dot norm to the power m, m is equal to 1 means rate dependent independent plasticity, m greater than 1. I have said m greater than 1, that is no more rate independent. There is no such straight limb, all right, it is strictly convex, right. So, it is as if that if you take now the flow rule sigma equal to the subdifferential of phi, then it describes a nonlinear viscously damped flow rule, right. So, viscoplasticity therefore is a broader framework. It is definitely a broader framework. In the limit of m going to 1, you actually still recover rate independence, right. So, mathematical well posedness. So, what did we see earlier? If there is a non-smoothness in my yield surface, then at this point the yield, the yielding can occur in any direction of the plastic flow, which is according to in this in this cone, normal cone. So, this is a valid direction, this is a valid direction, this is a valid direction, these are all valid directions for plastic flow. This is not mathematically well posed, because you expect in mathematical well posedness that given any stressing of the solid, any forcing applied to the solid, you should be able to solve for the deformation uniquely. This is no longer the case. This is physically all right, but mathematically not, right. So, we have now a mathematical well posedness if we deal with because of the smoothness of both phi and phi star, right. Many treat therefore from this angle, if you look at rate dependence, then many authors, many very important authors also think of rate dependence as a numerical regularization of rate independence. This is true provided you completely discard the physical aspect of it. What I try to mean by that is that rate dependence is physically meaningful as well, that we have already seen, right. So, therefore, transition from a rate dependence is basically given by all this, So, phi star is no more IC of sigma, right. It is no more an indicator function, that I have already told you. There is no such normal cone. The normal cone may be still there, but it is only consisting of only one element all the time, and so the strict convexity does all the job, right. So, basically we are now interested in these properties of phi. It is convex as before, non-negative, okay, no problem. Phi 0 equal to 0, it was earlier also true, right. But what was not earlier true for rate independence, now true, is what is called superlinearity of phi. That means if phi is a function of v, in this case any velocity like quantity, epsilon p dot is a velocity essentially, right. Then as this v tends to infinity, its magnitude tends to infinity, phi v by modulus of v must also tend to infinity. Earlier it was not the case. For linear limbs, you see this will go to 1, but if phi v is of the form v square, v transpose v, right, then what happens? As v tends to infinity, you will be getting v square by v, right, that sort of a thing, right. So, that goes to v, v tends to infinity means the whole thing will also tends to infinity. That means phi v must have a superlinear structure in order for this to be true, right. So, this is one of the important issues associated with rate dependence, right. So, we will be talking about these models better in the next class, because already we have been spending over 30 minutes for this lecture. So, essentially what we will be discussing in the next lecture is that we will be talking of several examples of such cases of phi which are there in rate dependent plasticity, but we will be emphasizing the Perzyna model of plasticity, right. The Perzyna model of plasticity is the most well known and the most useful for engineering plasticity applications, and we will start with phi star there and then consequently see the structure of the potential phi as we did for the Drucker-Prager model, right. We will always be starting with phi star because that is the easier construction. Then we will be discussing the FEM implementation for this in full detail. Basically, we will be deriving the consistent algorithmic tangent operator, which goes into the construction of the modified stiffness information in finite element implementation of this plasticity, okay. So, also we will be seeing the connections in future between viscoplasticity models and the famous Moreau-Yosida regularization. All of these are coming up, so there are very interesting things afoot. I hope you keep yourself engaged with the same vigor that probably you have been doing so far, because there is a lot more interesting information that will come up soon. So thank you for your patient hearing. I hope you're enjoying this, so I'll see you in the next lecture. Thank you.